Hello everyone, I am Mohammad Faisal Khan from NSDCS Research Group, Department of Electrical Engineering, IIT Indore. Today I will present our work titled RAMAN Resource Efficient Approximate Posit Processing for Algorithm Hardware Co-design. This work focuses on designing a resource efficient AI accelerator using approximate posit arithmetic for edge AI applications. In this presentation, I will briefly discuss the motivation behind this work, the research gap, our proposed RAMAN architecture, hardware and algorithm co-design methodology, experimental results, and finally the conclusion and future scope. Edge AI applications such as autonomous drones, smart surveillance, industrial IoT, humanoid robotics, and image recognition require real-time processing with limited hardware resources. These systems operate under strict constraint of power, memory bandwidth, latency, and silicon area. Therefore, efficient AI hardware acceleration has become extremely important for practical edge deployment. Deep neural networks mainly consist of convolution layer, fully connected layer, pooling layer, activation, and normalization layer. Among these operations, convolution and fully connected layers dominate computation because they rely heavily on multiply, accumulate, or make operation. In modern AI workload, make operations consume the majority of computation cycle and hardware resources. Therefore, optimizing make computation directly impact accelerator efficiency. This slide explains the key motivation behind our work. As AI model become more non-linear and complex, the number of make operation increases significantly. Recent DNN workload show that make operation dominate overall computation. At the same time, many AI applications are naturally error-resilient, meaning small arithmetic inaccuracies do not significantly degrade final accuracy. This opens the possibility of using approximate computing technique to reduce hardware cost while maintaining acceptable AI accuracy. The main contribution of this work are: first, we propose a POSIT 8,2 based approximate Mach engine. Here 8 is representing bit width and 2 is the exponent size. Second, we integrate approximate multipliers inside the POSIT data path to reduce area and power. Third, we design a scalable vector execution unit or VEU for AI acceleration. Fourth, we perform complete algorithm hardware co-design analysis to study the impact of hardware approximation on application level AI accuracy. Overall, the proposed design achieves up to 46% LUT reduction, 35.66% area reduction, and 31.28% power reduction compared to the baseline Mach architecture. So instead of conventional floating point representation, we use the POSIT number format. The key advantage of POSIT arithmetic is dynamic precision control using the regime field. Compared to FP16 and FP32, POSIT arithmetic provides better dynamic range, improved numerical efficiency, and reduced hardware overhead. In particular, POSIT 8,2 offers a good trade-off between accuracy, resource utilization, and throughput. This makes POSIT arithmetic highly suitable for resource-constrained edge AI accelerators. This slide presents the core architecture of the proposed REAP Mach engine. The architecture consists of 6 major stages: decode, multiply, alignment, accumulation, normalization, and encoding. The critical stage is the multiplier block because it dominates area and power consumption. Therefore, instead of using a fully accurate multiplier, we integrate approximate multipliers into the POSIT data path. The POSIT decoder extracts sign, exponent, mantissa information. Then the approximate multiplier computes partial product with reduced hardware complexity. After accumulation and normalization, the final POSIT output is encoded. By strategically introducing approximation only inside the multiplication stage, we achieve significant hardware saving while maintaining acceptable inference accuracy. In this work, we evaluated multiple state of the art approximate multipliers including ROBA, drum, ALM, RAD 1024, Mitchell based multipliers, and DRLM. We compared them using FPGA and ASIC metrics such as LUT utilization, delay, area, and power. Among these approaches, DRLM showed strong hardware efficiency and was selected for integration inside the proposed REAP-MAC architecture. This slide presents the impact of approximation on hardware resources. The baseline accurate PDPU design requires 979 LUTs, 9579 square micrometer area, and 6.83 milliwatt power. Our proposed REAP-MAC reduces LUT utilization only 526 LUTs. This corresponds to 46.28% LUT utilization, 35.66% area reduction, and 31.28% power reduction. Importantly, these improvements are achieved while maintaining acceptable computation accuracy. Here we compare the proposed MAC unit with recent state-of-the-art MAC architecture implemented in 28nm CMOS technology. The proposed design achieves 0.006 square millimeter area and 20.28 milliwatt power consumption. Compared to prior works, our design demonstrates strong hardware efficiency with lower area and competitive power performance characteristics. This validates the effectiveness of approximate posit based computation for AGI acceleration. This slide presents the overall vector execution unit architecture. The VEU contains multiple MAC units operating in parallel. The architecture includes input feature buffers, wait buffers, output buffers, runtime scheduler, and control logic. The scheduler dynamically allocates workloads across MAC units for efficient hardware reuse. This modular architecture supports scalable AI acceleration for workloads such as CNN, transformers, and fully connected neural networks. This bar chart showing the comparison of area utilization with state-of-the-art MAC approaches and comparison of energy consumption with state-of-the-art MAC approaches. One important aspect of this work is the algorithm hardware co-design framework. Instead of evaluating hardware independently, we jointly analyze hardware approximation, quantization, and AI model accuracy. The workflow includes training, quantization-aware approximation, RTL implementation, FPGA validation, ASIC synthesis, physical design, and layout generation. The fabricated REAP-MAC layout using SCL 180nm technology is also shown on the right side. This complete flow ensures that hardware level approximation does not significantly degrade application level AI performance. To conclude, we proposed RAMAN, a resource efficient approximate posit processing architecture for AGI acceleration. By integrating approximate multipliers into a posit based MAC engine, we achieved up to 46% LUT reduction, 35.66% area reduction, and 31.28% power reduction. Future work includes integration into larger AI models, system level accelerator evaluation, data movement, power optimization, and deployment within spatial accelerators such as Iris. Thank you for your attention. I would be happy to answer any question or suggestion. Thank you.